So it's Sonia May. We go on with suspension.
Good afternoon, ladies and gentlemen. I'm Sonia May. I started my PhD 8 months ago at the Max Planck Institute for Dynamics and Self-Organization in Göttingen. And I'm delighted to have the chance to talk to you today about some preliminary measurements we've made on a driven dense granular suspension where we're trying to measure at the same time the granular temperature and the viscosity. This is how we make our driven suspension, or how we drive it. We have glass beads of diameter 250 micrometers. We have water flowing in through the bottom here, up through a porous brass plate, up through the glass beads and then out of the top. So just to let you know what these, what this looks like when it's fluidized, mount please. I hope this shows up also on the beamer. Anything coming? Right. So I need to stop this here. So this is just a camera at the side. You see the grains moving around inside the water. It's very dense. And this is actually the cute thing about using these fluidized beds is that simply by tuning the flow rate of the water we can mess around with our volume fraction of our glass beads, and especially interesting for us, we can look at this very dense regime here where we might expect to see some glassy type behavior. So first of all, our measurements of kinetic granular temperature. We use a method called speckle visibility spectroscopy, which in principle is very simple, but I'm sure I know a number of you have tried it, and unfortunately in practice it's not so simple. Here we have the fluidized bed with the grains in it. We shine a laser through it, and the laser is multiply scattered by the grains. These light paths recombine and interfere to create a speckle pattern at the other side. And as these grains move around, the paths change, and the intensity of individual speckles changes as a function of time. I'm going to show you another little film. This is also just a camera at the side of the fluidized bed with a laser shining on it, and the laser is shining on it all the time, although initially you won't be able to see a speckle pattern because the integration time of the camera or your eyes is so high, is so long in relation to the movement of the grains that at first you don't see the speckle. Then what I do is I switch off the flow of the water. The velocity of the grains, pause it here while it appears. The velocity of the grains decreases, and then suddenly the laser speckle pattern appears. And as the grains movement is slower, then the speckle pattern becomes more stationary. You see also some bulk rearrangements. To illustrate how this method works, how you can get the kinetic temperature from this, the kinetic granular temperature from this, I show here the intensity of two particular speckles, plotted here in red and blue, as a function of time for this short exposure time, 0.1 millisecond. These two speckles are adjacent to one another, and you can see that they're not correlated. What happens if we increase the exposure time is that we're effectively low passing the speckle, and we use this smoothing out of the data with exposure time to obtain the kinetic temperature. The variance of the speckle pattern as a function of exposure time is given analytically by this expression here, where here this beta is the so-called inverse speckle, which is how many speckles you have per pixel on your camera, and the idea is to try and get this fairly close to 1. The exposure time here, of course, and the only other parameter flying around is gamma, which is a time scale which corresponds to the time scale of the movement within the dense granular flow. So in order to get an energy scale out, we need not just a time scale, but we also need a length scale. This L star is the photon, so-called photon mean free path which corresponds not, as you might first think, to the length between subsequent scattering events, but usually comprises a number of scattering events because the photon, rather the light path, has to decorrelate. Unfortunately, measuring this L star is a bit tricky, and it's a work in progress. So, down please. Yes. So I can't show you directly the true granular temperature. I can show you how we obtained gamma and beta from our speckle patterns. So here we have the variance of the intensity of the speckle as a function of exposure time for various flow rates. So this is the highest flow rate, this the lowest, so this is the highest volume fraction. These black lines here are fits to this expression I showed you before, where beta, being simply a geometric parameter, is the same for all fits, and we obtain then as our measured quantity gamma. So here I have to ask you to suspend your disbelief, assuming L star is constant, and there's no reason really to think that it need be for varying volume fraction. This is what the kinetic granular temperature looks like as a function of volume fraction in this rather dense regime. And what we very nicely see certainly is the trend that as we're putting less energy into the system, as you might expect as it gets denser, the temperature goes down. So far so good. Now let's measure the viscosity, and we do so using a torsion pendulum. This is a rod with a ball stuck on the end of it, and the ball is coated with the same type of glass beads that we have in our suspension. This rotates this way about its axis and is attached rigidly here to this construction here. Here and here are the wires. We drive it magnetically, and we detect the very small deflections of the pendulum just by reflecting a laser off a mirror here onto a 4-quadrant diode. So here we have the equation of motion for a driven torsion pendulum. We have our driving torque here, which is sinusoidal with driving frequency omega. We have the deflection angle theta, the moment of inertia, this damping term here, which is our measure of viscosity, and G, which is the torsion constant of our wires here. By doing a couple of pages of mathematics, we have an expression for the real part of the susceptibility, in which we have the driving frequency, the natural frequency of the pendulum, again this moment of inertia, and our interesting parameter here, alpha, which is equivalent to viscosity. We drive the pendulum at frequencies between 2 and 20 hertz, and of course we look at the resonance curves, and here I would like to show you a few. This very sharp one here is just for water. Blue, green and red are for decreasing flow rate, so increasing density. The dotted lines here are fits to this expression here, with the moment of inertia the same for all the fits, but unfortunately the resonant frequency seems to have a small shift that I can't explain just at the moment. So from these fits we obtain alpha as a function of our volume fraction, and what we see very nicely is that as the volume fraction increases in this dense regime, something very exciting happens with the viscosity. It appears to diverge. And if I can just remind you what our temperature looked like as a function of volume fraction, what we're seeing is that as the suspension gets cooler, its viscosity appears to diverge. And this, we think, could be a signature of glassy type behavior. Thank you for listening.
Questions? Yes, Tom.
I just want to give you a warning here. I don't think you're measuring granular temperature. You're measuring unsteady particle velocity. And you have to be very careful about that. For example, liquid fluidized beds, I didn't see this, but they're susceptible to regular density instability, where particles move apart and move together. That is not granular temperature, that is unsteady velocity. A granular temperature is something which takes one particle and the particle next to it and makes them collide or pull apart. So if I tried to explain this yesterday, put two things on my hand and move them up and down, they have a zero granular temperature but positive unsteady velocity.
Right.
And in order to get and with the speckle technique, it's as far as I can figure out, it's impossible to separate the two. So I'm just a second question, how densely packed were the particles you stuck to your sphere?
Yeah, we tried to get a monolayer, but I'm afraid it's really
No, you
difficult.
don't want that at all. You want to space them out about a particle diameter.
Why is that?
A monolayer is almost circular. It's almost a flat surface if you look at the outside of it. But if you stick them on there and space them out about a diameter, then you get a really rough surface.
How do you suggest I do that?
What?
How do you suggest I do that?
Well, how big are your particles? I
250 microns.
Okay, well, the only way I literally did have my student do it by hand when I was doing shear cell studies many years ago. And 20 years ago.
Don't get students like that anymore.
But those were slightly larger. Those were more like millimeter size. But that is really the best way to do it. You might consider sticking on, however you stick it on, then take a pin and knock a bunch of them off.
That would be easier, certainly.
Some question, yeah.
Is this little plateau of alpha as a function of phi, and which is reflected through this rather abrupt drop of T kinetic, is it really, I would have expected this to be a real phase transition.
I didn't really want to get too excited, bearing in mind how preliminary these
But you
results are.
noticed.
Say this is a phase transition. And this, because we haven't put the L star in it, I wouldn't like to say, oh look, something special is happening at 58 or 57.
But the alpha is very, very meaningful.
I think the alpha is very exciting.
Thank you.
Yeah, come on.
Could you measure particle pressure inside?
Particle pressure. We are building a little setup which is basically a straw full of water with a kink in it and a net at the end, with the idea that we can put it into our fluidized bed, then fluidize and use this to measure pressure. But this only seems to work for the stationary packing. So we fluidize a bed, we switch off the water flow, and we have a well-defined packing fraction. But of course these measurements are dynamic, so it's not working yet.
It's a comment more than a question, just endorsing what Charlie has just said. There are lots of papers coming out at the moment on using laser Doppler or related techniques or speckle methods to measure transient velocity changes in fluidized systems, and then immediately move on to calculations of granular temperature. As Charlie says, that's totally misleading. I've been involved recently in some rebuttal with some paper review for chemical engineering science, but I also lost the argument. They're going to publish the paper. They've got some very high values of the granular temperature, not having corrected their data sets for changes in local fluctuations and voidage. You really do need an independent angle on voidage fluctuations and pore pressure fluctuations in order to be able to separate out the two.
Well, I would
totally concur with Charlie.
I would answer this in two ways. First of all, if this really is something like glassy behaviour, then we would expect dynamical heterogeneity. So we would expect really maybe even to have fluctuations in density. So this is something important to look at. The other thing is this torsion pendulum. We chose it for a reason. The idea is that we use it to measure the fluctuation dissipation granular temperature so that we can compare two.
Sure.
To find out what's going on there.
Good.
But thank you for your comments.
Okay.